All right, so let's look at the example today. Okay, so I'm going to do this a bit different. So let's say we have a cantilever beam. This is kind of similar to what you had to do for the previous assignments. In this case, we know the length of the cantilever beam is 400, and all the dimensions will be in millimeters. Okay. All right, then you have one force acting down here that is equal to 13 kilonewtons. And you're gonna have here a side force this way, which is equal to 9 kilonewtons. Okay, so let's say this is X. Y, and this would be then Z, okay? All right, so now let's give information about the cross-section. So the cross-section last time, I think we have been calling this BF, no? B flange is equal to 150. Scale. I'm not going to do it to scale, just I don't think we do good. All right, the height of the whole beam is 75, and the thickness, let's say T web, T flange, will be 3 millimeters, okay, for both of them. 13, sorry. 13 millimeters. Okay, and let's say we have a point here, B. Is located at 60 millimeters from that end. Okay, so the question is to determine I call it normal, but I'm also going to call it bending. And shear stress. This is run out of ink. Okay. At point B. All right. So let's start by taking away. You don't need to do in this order, but let's do in this order for this time. Let's first take care of the cross-section properties, no? The CG and the I. Yes.
Where along the length of the beam are we finding the stress?
Okay.
Finding the max.
Correct. So good question. So determine the very good question. The max, normal, and shear stress at point B. So very good question. So just looking at it, where should be the maximum? And it probably will be here at the wall, no? Okay, but I mean, we'll have to do the study. So first thing we're going to do, so we don't have to go back in the middle of the equation, is to find the cross-section properties. So basically means we're going to find the moment of inertia. So by now you should be kind of experts to do these ones. You have done this enough. So here we need to be careful, because this will be bending about what? What will be here if we do the cross section here again, the little figure. Okay, so due to symmetry, we know the location of the neutral axis, but what will be here, this over here, this will be what? Z, Y, no? So in this case, we need to find Y. Due to the 13 kilonewtons, this will be bending about which axis? About the Z, no? Okay, so we need to find, because of this one, we're gonna have to find the moment about the ZZ. And then due to the 9 kilonewtons, it will be bending about which axis? About the Y, no? Yep. So IZZ will be equal to what? I'm gonna start putting values. I think maybe a little bit faster. So the way we can do this is we can do the one of the whole cross section, no? And then we can get rid of these two pieces, no? Like we did on the last example. So this will be equal to what? So we do that in meters, would be 1/12 of 0.15. Okay, would be the BF times the 0.075 cube. So this will be the whole thing. Now we can eliminate these two parts over here, no? Minus twice those two sections will be what? 1/12. So here, I might need here your help. Well, what will be this? This will be 150 divided by 2 minus 6.5. So 75 minus 6.5, 68.8. 68.8. 68.5. So it would be 0.0685. And the height will be 75 minus 26. 49. 0.049 cube. Okay, so I have the result for this, but if you want to go and check it, this gives you IZZ equal to 3.9303 10 to the minus 4 raised to the 4. Okay, next we need to find what the moment of inertia about which axis? YY. So now it will be about this axis. Well, let's first do the middle part. Okay, the one here in the middle. What would that be? For now, this would be the base, no? So this would be will be, wait, this would be, okay, so what would be that distance would be the 0.49? 0.049 times, then would be the thickness, no? 0.013 cube. So we're doing here the meter section, no? Okay. Next, we'll do twice the one at the top. So it should be equal to what? 112. Remember now it's like if we look at it this way. So the base will be the thickness. So 0.013. And the height will be, what was the length here? So 0.15 cube. And if we do that calculation, you get IYY equal to 7.3215 10 to the minus 6 meters to the 4. Okay, I mean, there's a fastest way to do this problem, but I'd just rather go and try to follow a procedure, okay? All right, in this problem, do we really need to find the reactions? We don't really need to find the reaction if we start from this end and make the cut over here, no? Okay, but let's just be methodical and say, okay, since I've already here the origin, let's say now would be on this step. Let's do here, let's do, so first thing, let's say would be free-body diagram in order to try to follow a procedure. So free-body diagram, we're gonna have here the 13 kilonewtons, 9 kilonewtons. So what are we gonna have over here? We're gonna have a reaction here. Let's say R. So that one, RY. What else are we gonna have? A reaction, let's say here. All right, XY, yeah. RZ. But most important, what are you gonna have? Okay, so we're gonna have a moment here, reactive moment MY, and a reactive moment what? MC. Okay. Okay. So next thing after free-body diagram, the following step should be what? Okay, go ahead.
Like do 2 separate free-body diagrams.
If you want.
Okay.
If you want, it's fine. Yeah. So in here, for example, now if we follow, for example, if we do summation, right. This one is not going to give you anything, but doesn't matter. If we do summation of forces on the X, what are you going to get? I didn't put it, but it should be, I'm not going to put Rx, I'm just going to put 0 equal to 0, no? If you want, you can put Rx, but. Now let's say we do summation of forces on the Y. What are you going to get? I can zoom out. That work? No. Out. So if you do on the Y, what are you gonna get? Ry. No, minus what? Minus 13 kilonewtons equal to 0. So basically, this is going to give us AY equal to 13 kilonewtons. And maybe I can squeeze one more equation here. What will be the next one we can do? Summation of forces on the Z will give you what? Minus 9 kilonewtons equal to 0, which will give you, what did I call it? A. It should be Ry, and Rz should be equal to 9 kilonewtons. Okay, remember this would be 0.4 meters. Jump here to here. Okay, next we need to apply the moment equations in order to find the bending moments at the wall, no? Okay, for the resisting moment. So let's see. So in this case, we need to take moment about which axis? I mean, we cannot even say it before, so. About which one you want to take first? Okay, let's see. So this is, just do one thing here. Let's call here this point R, if you don't mind, just to make, I know it makes no much sense to call it R, because now that I take the moment equation, what do you need to specify when you take moments? About which point you're taking it, so put R over here, and then we can put here on the outside parenthesis saying about the Z axis. So this is an R, okay? I know it's not clear. This should be R. Okay, so if we take moment about the Z, which one of the forces is the one creating the moment about the Z? Ry is at point R, so can Ry create a moment? Okay, so what should be the force creating the moment? What about Z? Should be the 13, no? Times 0.4, would that be clockwise or counterclockwise? Will it be in the direction or opposite direction? So then that means negative, no? Yep. Okay, and mz we plot in positive, so it will be plus mz equal to 0. So this basically will give that mz is equal to, I think this is equal to 5.2 kilonewtons meters. All right, and next, what do? We do something similar. We take moments about point R, but this time about which axis? About the y-axis, okay? So similarly, this will give us what? So this first we'll have my, let's start at this one, and then what? The 9 kilonewtons will also be creating a going clockwise. Yeah, so you're absolutely right. So here I did the mistake here, sorry, on the figure. It should be counterclockwise, okay? On the figure. So it will be negative, correct? So negative minus 9.0.4 equal to 0. This should give my equal to 3.6. I mean, so far they should be pretty similar to the last assignment you have, no? This problem would be practice for that. I'm just adding here. Okay, so now that we have that, let's say if you needed to do let's do the whole thing, okay? We might have time. We should have time. I don't stop too much. Next thing would be to do shear. And then the moments diagrams. Okay, so in here, yes, I would do like you suggested initially, I will break this into 2 different planes. So what are the 2 planes we need to study here?
XY and X.
So let's see, XY. So let's say first XY plane. Like one, where we look at the XY plane. I mean, let's do it right away this way. Let's do the cut. I'm not going to do a figure. Start initially. So we look at the XY plane, then what do we have? We're going to have here RY that was equal to how much? RY we had equal to 13, correct? Okay, and what else we need to put over here now? Then which other moments we need to put? But the MZ, no? So the MZ would be MZ we had equal to 5.2. So now we do this, what we have here, B and M. Okay, this should be straightforward. You almost don't need to do the equations, but let's do by detail.
You skip finding the whole reaction side and then just immediately do the cut and then you face it off the right side.
Correct. That's what I said initially. You don't have to find the reaction. Okay. So you'll be fine. Yes, if this time you don't find the reaction and do it here, you're fine. This will be the same. I agree with you. Okay. That's what I'm saying. I'm not doing this the more efficient way, but I'm just doing the structure. Okay. 2 different procedures. All right. So over here, we start from this end over here. So this will be here again, X. All right. So we do summations of forces. On the Y equal to 0, what are you going to have? Ry minus V equal to 0, which is going to give you that V is equal to 13 kilonewtons. Okay, so for procedure, I'm not going to put about which axis this time. I'm just going to say about the cut. What should you have over here? You're going to have, so the MZ plus what? Plus M, no? And then what will be the rest? Minus V, correct, minus Ry X equal to 0. So you're perfectly correct. So that means that I'm going to put it here. I'm going to jump one line. M will be equal to what? So Ry is 13. So it will be equal to 13X minus 5.2. Okay, so we needed to do a quick figure for this. So this is X. This would be Vy, the Y direction. What would you have? Shear diagram will look like this, but this would be 13 kilonewtons. And what should you have for the moment? At X equals 0? Sorry, at X equals 0 should be equal to what? 5.2, and what should it be at the tip? 0. So we have here, if you want, the straight line. I think that's exactly what you had on the assignment, no? And this would be here 5.2, okay? Or negative 5.2 if you want. Okay, now we do exactly the same thing for the other plane. What would be the other plane? Look at the figure. We did the XY plane. What's going to be the other one? XZ plane, no? Okay. So if we follow exactly the same steps that we have done, let me make sure I follow the same steps. So we have the X plane. I'm going to do the figure again, kind of similar. B M. This time, let's see what we have. R was 9, no? RZ is equal to 9. Okay, RZ, put RZ here. And this time we're going to have the moment equal to what? To 3.6. So what's positive? So counterclockwise. Well, no, this needs to be on the same direction. So otherwise, it would be adding each other. So careful here. Okay. So and this should be the moment about which axis? Yeah, about the Y, no? I mean, really, it's not that important, this, but cut. So here we do summation of forces on the Z. So this will give us what? 9 kilonewtons. Oh, I should have put Z, doesn't matter. Minus V equal to 0. So V will be equal to 9 kilonewtons. and summation of moments about the cut equal to 0. This will give you what? M minus my, that is what? 3.6. Oh, okay, here we have to be careful, I think so. Okay. Yes, it's going to be a plus, but let's move to the next step and then we see here. So let's put the plus. Because really this is going on the other direction, no? The way we put it before. I mean, let's finish then and then we'll go back to study the sign. So 3.6 and then would be what? The moment created by this one, which this one will be positive or negative? This one now is going clockwise. Okay. So it would be minus nine x equal to 0. So this will give you that m, and I'm going to go back now to look at the sign. Will be equal to 9x minus 3.6. Okay, guys, so for the confusion, sorry, the reason why I did this way, okay, is because remember this class is based on what? In statics, no? So this must be equal to 0, no? Yeah, but when we calculated the moment here, this m really is going in what direction? So it's going really on the opposite than this one, no? So if I do the arrow this way, then this should be equal to negative 3.6 if I do the arrow this way. If I do it down, then it will be positive. Does that make sense or no? Okay. So let me then put the way it's plotted, then this should be negative here, okay? The way it's plotted. Okay. That's the reason. Okay. So at the end of the day, if we do again a very quick shear and bending moment diagram. These are very simple, okay? I'm doing exactly the same sketches. So this should be equal now to 9 kilonewtons. And here we're gonna have something similar as well to the one we had before. X and M. Okay, and this should be here, the 3.6. So it's very similar to what we did before. Okay, so I did something very long, but all this stuff, what do we need to do? Find the bending stresses or normal stresses at point B, no? Point B is located here at the wall because that's the maximum location. So let's say the maximum values. Let's say the maximum, values are located at the, instead of wall, let's say the fixed end. So in that wall, what are we gonna have? From the first figure, we're gonna have what? The V The Vy, the maximum Vy would be equal to what? 13 kilonewtons. This one is gone again, so 13 kilonewton. Then the Vz, 9 kilonewtons. And then the maximum moments would be what? So mz will be, so my, mz, so I guess my is the one that is 3.6 now. .6 kilonewtons meters. I'm just putting absolute values, and the other one would be 5.2. Or if you want, you can put negative values. I don't care at all. Negative values. Because at the end of the day, we're not going to look at the sign of the stress by looking at the sign of the moment, but by looking at if it gives tension or compression, no? Okay. So basically, that's loading. This is the important part. This is the loading needed for calculations at point P. Okay. And all this stuff almost identical to what you did on the previous assignment, no? Oh, another thing, sorry guys, if the I'm not getting back to you the assignment yet, is because the grader went to is part of the eco car. So supposedly they had a convention all last week about the eco car. So it will give you back, but the assignments, I don't know when, but pretty soon now. But anyway, I posted the solutions, no? Videos of the solutions. Did you see them? Okay. All right, so yes. It doesn't matter at all, it's just notation, okay? So what happened is that in this case, really shouldn't matter. Both of them go out at the same time, we'll have a problem. So if the structure is symmetric, all right, what does that mean? Let's say this is Y, this is X, okay? What would that mean if the cross-section is symmetric? Is that I, X, Y is 0. So what happens is that if it's symmetric, you might see the notation just of this one. Either one, you see? Or I, Y, Y. But if it's not symmetric, let's say it goes, I think we did one example that was kind of like that. Then what happened? The I, X, Y is different than 0. So you need to, you know. Then, Johnny, when you have the two of them, you make sure that you show that you will use this notation. It's just notation. There's no difference at all. You understand that it's just notation? Yes. Okay. Okay, so let's find here now. Let's first do the normal stress. Okay, so for the normal stress, what would be the equation we need to use? The normal is in what direction? It's on the X, no? Along the length. Correct. Perfect. So sigma X. Now we have here a moment. Let me just do a figure of the cross section. It might help a little bit as well. Let me do it here. All right, so we know this is a neutral axis. This will also be here, neutral axis, but also this will be the axis. I think that we call this one the annex, no? Yeah. Z and Y, sorry. I write something and I say something different. Okay, so if we first look at the effects of the moment created by the moment Z. Z is creating bending about which axis? About this one here, no? Yeah. So what should be now if so this one is created about this one, so we need to calculate here, let's say point B is over here. So here we need to put Y, no? Okay. And this is bending about which axis? The ICC, no? So this will be the first component. But we have another moment, which is the MY. So this one will be bending about which axis? Or the Y. We look first at the motion, this one up and down, now we're looking at this one, no? So this is bending about the YY. And this time the location will be what direction? This should be Z, no? Yeah? Okay. And again, I put here a plus because I don't care. The value will be given by knowing if it's tension or compression. We're not going to pay attention to much of those signs over here. Okay, so before we go and apply the equation, maybe it is good now. Okay, maybe let's go back to the initial figure. Okay, so which one of the forces here is creating the moment about the Z? Is the 13, no? Okay, so the 13 will be causing what type of bending? It will be going down, no? Yes? So the one would be like what they call the sad face, no? So then the top would be in tension or compression. Tension will be, the top will be in tension. P is at the top. So that means that that term will be tension. Okay? All right, so it will be tension for this case, so tension. That means positive, but I'd rather see tension than positive, okay? Now, what about now let's look about the moment about the Y. Now this will be bending towards, against that direction. Yes, so this side will be what? Tension or compression? This side will also be in tension, no? Yes? Okay, so tension and tension. So basically, if you want, you can put here positive, positive. Okay, so the next thing we need to calculate is what will be Y at point B? What would be Y? I don't know. What was Y? Okay, so would be at point would be so 75 over 2. Would be the 37.5, no? So 0. Okay, so 37, let's put it this way, 37.5 millimeters, which will be, okay, or Y equals 0.0375 meters. And what would be Z? That's the one that's a bit more complicated because we know that distance here is, I think that was 60, no? Correct, 150 divided by 2 minus 60. So 75 minus 60 should be 15, no? 15 millimeters, or Z equals 0.015 meters. Okay, so let's say substituting, let's call this equation here capital A. So substituting back into A, we're gonna have sigma X equal to MZY divided by IZZ. I'm gonna have to zoom a little bit, I guess. Plus MYZ divided by IYY. This will give us watts, so that's watts. So MZ is, be careful because here is kilonewton, so we have to multiply. So what was all the data for this? I'm looking now at this data here. So MZ is, don't put the minus, so 5.2, 10 to the 3 times 0.0375. And if you can give me the values separate, would be better. Divided by IZZ, that is 3.9303, 10 to the minus 4. Do you have that value? I have the final value, but I don't have this value. So doesn't matter because it will be just divide them by 10 to the 6, but it's fine. You can give it that one. So 49.0. 49.0. That's it. 61. 49.61 10 to the 6. Yes, no?
Yes.
49.61 10 to the 6. I write it that way. And then we do the next one. That will be what? My we say is equal to 3.6 10 to the 3. That's why don't put any sign, because we said the sign comes from tension compression, no? If you start putting out signs, you're going to mess everything up. So we do now Z. Z we say is equal to 0.015. Yeah, I'm having so many pieces of paper in front of me. So divided by the IYY, that would calculate it to be 7.3215 10 to the minus 6. So I guess this value should be about 8 or something, 7 points, something. 7.276. 376, 10 to the 6. So at the end, that means that sigma X is approximately, to round it off at the top, we get about 57. I think it would be very close to 57, no? Exactly 57? All right, so let's say 57 megapascals. Okay, so this would be the maximum normal stress at P. Okay, the next thing we need to do is what? To find the maximum shear stress, no? Not to find not the maximum shear stress, to find the shear stress at point B, no? Which should be the maximum as well. But it's equal, the same all over the cross section. Yes, no? Remember, V was equal, no? All right. So let's look now at the shear stress. Once again, let's do a figure. Oh, let's do a figure. Again, I'm going to do a bit figure because now that we talk about shear, we might have to do this a little bit bigger. This is point B. So I'm going to do the forces here on the side. I don't want to do them on the figure. All right, but let's say we have what? I think we had, so for this cross section, what do you have? V, Y. The one going up was equal to what? Is that 13? And then the one going on the Z is 9, no? Is that what we had? Okay. So again, you see that this would be really axis, and if you want to be accurate, it should be Y, Z. Okay. Okay, so each one of these two forces, VZ or VY, can supposedly create a shear, no? Yeah. Okay, so let's start first by, let's first look at the one that is 9. Here's so VZ. So let's look at VZ. So we look at VZ, we're going to have shear equal to, I put the general equation, okay, over IT, then I'm going to put some more detail. All right, so let's see. Now we come here to the kind of is equal to our VZ, which is 9. Okay, now he's the one that sometimes you get confused about this one. Which one should we use if we use the VZ? Which Y? The IYY or IZZ? Perfect. IYY, and IYY is equal to 7.32, 15, 10 to the minus 6 meters to the fourth. Sorry, I move it a bit to the right. I'll zoom a little bit. Remember, we're starting by this one. So now what would be, okay, let's do this one, T, let's do Q. Q, we need to find it. What would be T? Really? The force is going in that direction. In that direction, what should be the area? If the force is coming this way, no? Here will be 0, no? At this end. All right? But now as you move inside, you don't have this area resistant, no? Okay? And because this is symmetric in this case, I mean, you can, let's look at it. We can do both ways, 2 ways. So what is T over here? T was all the time, I think was 13 millimeters. So 0.013 meters. And in this one, Q, what is the approximation we say to do this one? Okay, so what would be the area then? The area of the other segment. So this is 150, this is 60, and this all this stuff here is T13, no? So that area would be what? 150. Oh, I should have done that in meters already. Minus 60, doesn't matter. Times what? So I should have done, okay. Let's do the other way around. So this is this times 13. This will be the area. And now we need to look at what distance? Distance from here to here. Okay, so we'll be so will be 150. Okay, the distance will be so if we do this, will be 150 minus 60 plus 60 divided by 2. No? Okay, or 150. Yeah, we can do 150. You say 150 divided by 2 minus 30. Yeah, we can do it that way as well. Correct. It's the same thing. So I don't have a number for this, so you don't have to give me the number. And this will be the distance over here. Yes. We are using the area for the highlighted section.
I got.
Wait, I mean, wait, but that's what do you? We are using this area here, the one that's in red. Okay, so we did 150 divided by 2, so this will be here, yes. Oh, so it should be 60 divided by 2. Yes. So let's see. I mean, I was maybe. So let's say it should be okay. So all the ones maybe instead of 150 should be 150 divided by 2.
It's just the area.
Yes, we just need this area here. Yes. Oh, okay. Yeah. So I did completely. Yeah. Sorry. So let's redo this one. I was completely off. I was complicated stuff. Okay. So let's go again. So let's do it now immediately. So what should be this? This should be then. The area would be 60 times 13. Good call. Thank you for paying attention. I was going too fast. Okay. And now we need to do that distance over here. So now that distance would be what?
Still 150. Still 150.
Yes, 150. Yes, that's correct. Minus 30.
I got it.
35,000.
Millimeters.
Okay. So this will also be equal then to what? 3.51 10 to the what? 10 to the minus 5 cubic meters, correct. Maybe I should have got 35.1, but it doesn't matter. Yes, sorry for that. Since I zoom. Okay, so we got everything now, no? All right. So that we have tau equals BQ over IT will be equal to, and this is 9 kilonewtons, so will be 9,000 times 3.51 10 to the minus 5 divided by 7.3215 10 to the minus 3 times 0.013. And for this, I think I do have a value. I have the details. You get about 3.32.
Yeah.
All right. So this should be 3.32 megapascals. Okay, the next one is going to be very quick. dy tau equals to VQ over IT. We have V equal to, how much was it, 113? I, this time will be which one? IZZ, I'm not even going to put it. But let's see. T, but it's more important here. What is Q?
0.
You are agreeing that here Q is 0. If you go here up, we always say that what should be the shear at the top, at the bottom? 0, no? There's no surface, so, and that's because Q is equal to 0. So really here we're gonna have tau equal to 0. That's because what do you need in order to do shear? Yes, because the area is 0. You need to have one surface against the other one, no? So in this case, what is the surface on top shearing will be 0, no? But even though the mathematical reason because the area is 0, the physical reason because you need to have one surface shearing in respect to the other one, no? So if you look at the force Vy, the shear should be 0 at the top and the bottom should be maximum in the middle. Yes.
So if the shear was not 0 due to Vy, would you just add the shear from Vy and Vz?
In this case, yes. When I say this case, it's because here we're looking at the shear due to Vx or Vy. You can also have shear due to torsion, and it has a different distribution. But in this case, for these two equations, you can add them together.
You don't have to worry about sign or anything like that.
You have to worry about the sign, but in this case, you can add them. In this case, you need to worry about the sign. We can do an example later on, but you need to worry about the sign. I will do it. Yes. You got a question? Okay. Yeah. So if you want, I'm not going to answer 100% your question today, this one, but let's say, Jenny, when you talk about shear, yes. When you talk about shear, all right, in an element, remember, what is the equation we use all the time here? Summation of forces equal to 0, no? Okay. So when you have shear due to something like that, generally the sign convention will be what? All this needs to be equal to 0. So generally, this would be, you can define what is for you your positive or negative shear, but it would be either this way or the other way. So this will be direction of the shear in one element. You see that everything is equal to 0, no? Okay. We have 4 minutes, so I'm just going to show you something. I'm not going to do it, and I might just, it will be on the video, all right? So for example, the shear is a 3D effect. So for example, shear can only be 2D, all right? You have 2D, if you, it's like having a block. When you deform the block, all the 8 sides of the cube are going to deform, no? Okay, so here we look at the shear from, if you want, the side of the block, but we could have seen at the shear from the top of the block, no? Yes? So if you look at the shear from the top of the block, let's see, what do I have it? So up over here, you see alternate calculation. If you look from the top of the block, then this would be the area that would be resisted, okay? So you redo the same thing over and over again, and basically this is what you will get for Q, which is basically the same. I mean, will not be the same, but because your T will be different this time, but you should get the same result. In this, if you look at the top, the thickness should be the whole length of the beam. All right. So I just put it here. It will be on the video if you want to look at it. So let me stop the video for 1 second, but we need to decide about the exam.